from Terklin on HVDC, VSC HVDC and transmission on renewable energy, part 2. The first part of this talk was actually just before Christmas. So if you would like to view this talk, then you can find this at the IET Northwest Midlands YouTube channel. That will be added on the chat, the link, or if you just go and search YouTube at the IET Northwest Midlands, you can go and see that and other talks, videos of other talks that we have done recently. So welcome to Zoom, and it's a bit different to the fact that we're not meeting in a lecture theatre. But I hope you're all sitting comfortably at home and you're ready for this exciting talk. So I'm Alison Griffiths, and I'm on the Northwest Midlands panel, and I work at Staffordshire University, and I'm the link between education and industry and the local network. So you will wonder, sorry, some of you may already be members of the IET, and some of you might be here because you're interested in the subject. So we're welcome to everybody, and also if you'd like to join us, there is a link again that will be shared in the chat button, and I shall do that whilst Terklin doing talk. There is a chat function, so if you did want to say hi, you can say hi. But we do request that if you would like to pose any questions to Terklin, then you use the Q&A button, which is located at the bottom of the screen. Now, the reason for that is that we can filter out all the questions from other comments. If there's other people in this call that you know, well, say hi, but because the chat isn't saved. The questions are saved, and at the end of the talk, I'll give Terklin a quick break, and my colleague Amelia, who will soon introduce him, will field the questions that you placed in the Q&A. And if there's any questions that can't be answered within the time of this Zoom chat, then this will be posted to the IET Northwest Midlands forum. And then the answers will be placed there also for you to look at. So I would also encourage you to go and download an IET CPD certificate from the website for your continuing professional development. More messages down there. Okay. So thank you for joining today's webinar. So also we had an event on professional registration this week, so you may be interested to have a look at that one on the YouTube channel. We also have journals, books, the Inspect magazine, ENT magazine, IET TV, so you can have a look at different lectures from different networks, and also the digital library. So I would just like to say that we do have an upcoming event on the 16th of March, which is about the ethics of autonomous vehicles. So that's going to be a really, really exciting one. I shall share the details of that at the end, and also I'll put the links in the chat. There is also another event coming up shortly. This one is through the British Computer Society, and this one is on Tuesday the 9th of February, and it's called AI for Digital Forensics of Investigation of Digital Media. So we're all using lots of digital media now, and as we know, it's easier to access this information. So digital forensics is becoming a hot topic. I'll give you the link. The videos are in the IET Northwest Midlands YouTube channel. I shall post the videos in the chat once I've handed over to Amelia. So now, without further ado, I would like to pass over to my colleague Amelia, who will be introducing Terklin.
Thank you, Alison. Hi, everyone, and thank you for joining us tonight from the Northwest Midlands IET local network. As Alison said, this is part 2 of Terklin's presentation, VSC HVDC and Renewable Energy Part 2. Terklin Sinulingga is a senior bid manager in the HVDC industry in UK. He's got more than 30 years of experience and he's held various senior positions within the commercial and project management side of business within HVDC. He's worked in various countries, including Indonesia, France, and the UK. He's written 2 books, so he's the author of a book which covers HVDC, LCC, and HVDC, VSC, and renewable energy, which he'll be talking about later on today. He's got more than 15 years experience as a university lecturer, visiting and delivering lectures in AC substation and in HVDC. Some of the topics in his book, the VSC book, will be covered in his talk today. Some of you have already asked if there is a link to the talk that he did in November. Yes, there is. We will be providing you with the link to the YouTube channel later on as Terklin will be delivering his talk. As Alison said, there is a Q&A tab at the bottom of our screen. If you do have a question, please put your question in the Q&A session. If you put your question in the chat session, I'm afraid that will not be answered. So please, can you direct your questions to the Q&A sessions? At this stage, I'll take this opportunity to introduce you to our presenter for today's event, Terklin Sinulingga. Terklin, over to you.
Okay. So I'm sharing now the file. Can you see? Hello?
Yes.
Okay. "30 years ago, we would never have imagined that renewable energy plant will be as prominent as it is today. The expected numbers of the renewable energy power plant are projected to exceed conventional power plant in the near future. Among the renewable power sources, wind and solar in particular have experienced a very high rapid growth in the past 3 decades. Today, I will talk about VSC and renewable transmission because as the number of renewable energy plants being built increases, the more likely an unstable network will develop if we do not manage well. I would like to talk about how VSC could enable renewable energy transmission, particularly onshore wind farm and solar energy, and make them reliable and safe for electrical network.
Terklin, you need to start the slideshow.
Yeah. So yeah, still not yet. Yeah. Later on this presentation, actually, I will present to you the economic comparison between HVAC and HVDC on the overhead transmission line network. Actually, I will start the presentation, but this is only preamble for my presentation here. So let's go to slide. Today's seminar, we will review renewable energy transmission, study engineering and VSC HVDC performance, factory testing, site testing and VSC warranty period, economic valuation, and comparison cost between SVAC and SVDC project. And then the last one, VSC HVDC with Renewable Energy Reference. The sixth topic actually has been discussed on 5th November. We will not review this today. Clean and renewable energy. Today, there is a requirement to meet their target for CO2 reduction. The electricity from fossil fuel is main contributor to CO2 emission. Among the renewable energy sources, both wind and solar energy have experienced remarkable rapid growth in the past 30 years decade. Renewable energy actually consisting of two parts, dispatchable renewable energy, hydro and biomass, while for non-dispatchable energy such as wind and solar panel. The presentation today will discuss only for non-dispatchable of renewable energy transmission, offshore wind farm, and solar energy. These two types of renewable energy with opposing electrical output. So if we see here, the wind energy here, we produce AC and then we convert to DC, and from DC to convert back to AC in order to be consumed. So very unique. So we start from AC, we convert to DC and AC and back to AC. While for solar energy, we produce the energy in DC, we need inverter to be converted to AC in order to be consumed by load, AC network. So both of solar energy here, wind energy and solar energy need a rectifier to convert the energy as needed. So for wind energy, we need converter from AC to DC and from DC to AC in order to be consumed. While for solar energy, we need inverter to convert from DC become AC. The objective today, we will review how renewable energy from wind turbine and solar panel is transmitted either through AC and or DC. What is the wind energy? Cut in wind speed, typically from 3 meters per second, the energy will be produced in wind turbine. And then by having the speed between 15 to 25 meters per second, we produce optimum power. And after that, for 25 meters per second, we call it cut out wind speed. The wind turbine should be stopped because it will damage mechanically turbine. The typical conventional turbine, the main component of turbine, generator, converter, and DC chopper. DC chopper here, the component, the purpose of DC chopper here, in case when the energy produced by a wind farm or turbine cannot be transmitted to AC network, let's say like in onshore, maybe because of fault, all the energy should be absorbed or dissipated By this, we need a component, we call it here, typically DC chopper. What is the turbine? Turbine here, there are 4 types of turbine. The first generation of turbine, wind turbine fixed speed. This is the first generation, maybe it was built by 1970. Turbine size small and very simple. And of course, maintenance is simpler because all stator here connected directly to AC system. The advantage for this wind turbine, easily disconnect during fault right through. Fault right through is in case any fault or because of intermittency energy. The second generation is called limited variable speed wind turbine through resistor. The difference here, the stator still connected directly to AC network, while for rotor connected to converter through variable resistor. The advantage here, by having variable resistor, it can produce higher power compared to fixed speed turbine. So theoretically, this limited variable speed produce more power than generator with fixed speed. The third one, variable speed through rotor. If we see here, the turbine, the rotor turbine connected through converter and converter back to back, from converter connected to AC, while for stator here, still connected directly to AC network. The advantage here compared to limited speed turbine, they still can more independent and controllable anticipate fault right through because part of turbine already been controlled by converter here. So the advantage compared to the previous one, we are able to anticipate fault right through. The advantage here, because the stator still connected to directly to AC network, difficult to meet grid code. So partially we can meet, but not fully. The last one, this is fully connected through turbine. This is the fourth type of turbine. The stator directly connected to converter and then connected to AC network. The advantage here, because all output turbine go through converter, the stator here, stator fully connected to converter, easy to meet grid code here. The advantage mainly because fully controlled by converter, generator control is complicated and converter quite expensive because we need higher rating of converter. How turbine produce the energy? Variable speed wind turbine generator connected to two-level converter. So when turbine produce the energy, it should be connected through converter. Currently, actually, there are 2 types of converter used in turbine. What we saw here, 2-level converter, but the turbine also can be connected to 3-level converter. We discussed about converter in our presentation in November. So from this converter, connected directly to AC network. So we need still DC chopper here, filter here, the function here to supply rectifier need and to dampen harmonic produced by turbine. Turbine configuration. There are 3 types of configuration of turbine. radial, ring, and star. Actually, from this brochure, we could not see the configuration. But actually, in the market today, most of turbine using a combination, either radial and ring type of turbine. So most of the turbine today using radial and ring type. Full right through. So in order to be compliant with the grid code, actually turbine or all apparatus connected to offshore should be compliant with grid code requirement, all for right through. What is grid code requirement here? This is example of apparatus, let's say like turbine, when they operate between 140 kV to 170 kV in continuous operation and in steady state. And then the operation between 49 Hertz until 51 Hertz. So during continuous operation, this is the rating we have to maintain. However, there is grid code requirement. In case there is a fault or in case the power down, maybe the frequency will be reduced between 48 to 49 Hertz, for instance. By this turbine or apparatus in offshore should be designed to remain in operation for 20 minutes, for instance. And then the same, when frequency down between 47.5 until 48 Hertz, the turbine or apparatus should remain in operation within 10 minutes. The same, when frequency above the continuous operation, say 51 until 51.5, the generator or turbine or any apparatus should be designed to remain in operation within 30 minutes. This is typical grid code requirement. But of course, from grid code requirement will not be same between one country to the other country, but this is once again typical requirement for to meet a grid code in the network. The configuration here, there are three types of configuration for turbine. Imagine this is cluster of turbine. So when we are using DC connection, the cluster of turbine connected directly to rectifier. From rectifier to be transferred the power through DC submarine cable to inverter station, which is located in onshore. So for DC system, actually used for the long distance. While for the second one, the cluster turbine directly connected to AC substation offshore, and by using the AC submarine cable, the power transmitted to AC substation onshore. Normally, this is used for short distance. The third possibility, combination of AC and DC. So 50% maybe can be transferred through AC, and then another 50% through DC here. So these three possible configuration. DBS or DC chopper. What is DBS? Dynamic braking system or DC chopper? Once again, by definition, when energy produced by turbine, in case any fault in AC network, the energy cannot be transferred to AC onshore. There is available energy which cannot be transmitted. For this should be absorbed or dissipate. So can be absorbed by DBS or DC chopper here. There are four possibility places to install the component either DBS, DC chopper. First of all, here, DC chopper or DBS installed in onshore DC converter station. This is example. Imagine here in offshore substation, converter station, we have onshore valve, and then we install parallel DBS. This is one possibility. And then the second possibility, we can install offshore DC side wind generator. Here, when we can see in this diagram. And then the third one, onshore AC side. So if we imagine this is AC, this is converter in onshore. So if we want to put onshore AC side, we can put absorber or DBS somewhere here. And then the last one, on offshore AC side. Imagine if it is still in offshore, we can install DC chopper somewhere here. How it works? When energy from turbine cannot be transferred, cannot be delivered to AC network, actually, in case any fault, for instance, emergency control panel will instruct station to stop energy. So if before fault, the power may be transferred 1 PU, and EPC will instruct to stop. Imagine, the EPC will instruct a converter or turbine to stop, let's say like within 4 to until 8 milliseconds. And at the same time, EPC will instruct DBS, dynamic braking system or DC chopper, to absorb the energy. So when the energy down from 1 PU to 0, so where actually the energy should be dissipated. So if we see from this scheme here, when the fault is there within 1.5 seconds, the energy is still 0, absorbed by DBS, and then suppose it will be recovered, the fault within 1.5 seconds, there are still excess energy where actually DBS still working. So between instruction, when they activated to dissipate, all energy will be absorbed by DBS or DC chopper. So now we move to, we finish turbine. So now we move to solar panel. There are two ways to utilize sunlight. One, we call it photovoltaic. Photovoltaic system converts solar light into electrical energy by utilizing solar panel mounted on rooftop or above ground. While the second one, concentrate solar panel, CSP. CSP here, CSP system converts sunlight to heat or thermal heat energy in form of steam rotated the turbine to generate electric energy. Today in the market, most of solar energy, we can say 80 to 90% using photovoltaic, the remaining only CSP. This is typical circuit diagram of photovoltaic. We have diode and resistor here. And then this is typical of how we produce the energy. This is the curve of current and voltage. And then this is the curve of power and voltage. Maximum power in this point, and then output energy sometime somewhere here. Solar panel, module consisting of many solar cells. So in this picture, we can see one module consisting of 72 solar cells. So imagine here, one solar cell equivalent to this, and then we have 72 solar cells with about the size almost 1 meter times 1.9 96 meter. The combination of module will form, we call it solar panel. The arrangement can be series or parallel connection. The more energy we need, the more module needed to form solar panel. Here example of solar panel. We produce still DC, but in order to be consumed in load, we need inverter here, converter. So we need inverter to convert DC to AC system. So for this, we always need converter. We could not directly connect from solar panel to the load. What is inverter? Inverter here equivalent to PCS if we see in the market, power conditioning system. The function here to improve operational performance and the network reliability during fault. So to meet grid code fault right through. So if we see here, this is the circuit of inverter. So inverter here self-commutated. So they can, by having this converter, we can produce rectifier, for instance, because we can produce rectifier at the same time, we also consume rectifier. At the same time, we also consume reactive power. And then the second function of PCSE to maximize the use of maximum power point of tracking, MPPT. What is MPPT here? From this curve, we can see this is theoretically maximum power can be produced by solar panel, but in the reality, we produce the energy produced somewhere in this between. The PCS function here try to maximize this point to going up to get more energy, electrical energy. Offshore connection here through AC. So we imagine here offshore cluster of wind turbine. Offshore wind turbine will be connected to AC collector station, which will be located offshore. From AC collector substation, the power, the power transformer will increase the power because we produce the voltage here, maybe medium voltage, maybe somewhere 33 kV. We increase the power using power transformer in AC collector station to be higher voltage. And then from convert AC collector, we transmit using AC submarine cable, 150 kV to onshore substation. What is AC substation collector? If we see here, from the design, AC collector substation consisting of many equipment. AC substation, power transformer here. So this is typical design of AC collector. GIS, power transfer, all equipment installed inside. Barrow offshore on England, AC collector Barrow, nominal power 90 megawatt, 132 kV, project operation 2006, number of turbine 30, and then each turbine with 3 megawatt capacity, cable distance to land 11 kilometer. So we can see here the distance to the land very short, yeah, about only 11 kilometer. This day, turbine generate voltage between 33 until 66 kV. So the highest turbine today, let's say Highlight X, can produce until 13 megawatt per turbine with the output voltage 60 6 kV. And here, typically for power transformer, we install 2 because if one node is not working, the second is able to deliver power. AC, we have limitation here. AC cable, AC submarine cable has a big capacitance value here. The longer cable, the more capacitance produced. At the end, we will produce only reactive power and the active power become 0. From this formula, we can see the longer cable, the more reactive power produced. This is typical curve for AC submarine cable. Typically, for power 575 megawatt with the voltage 400 kV, typically we can only transfer 40 kilometer. And then when we install reactive power compensation on both sides, on offshore and on onshore side, we can extend the distance theoretically 80 kilometer, but normally will not be stable. This is the limitation for AC because of charging current. While for DC, we don't have frequency here. The frequency 0. So we are not limited by the distance. So theoretically, we can deliver the power for long distance. How it works? So imagine this is photovoltaic. We connect to PCS inverter. From inverter, we connect to substation solar panel using cable or conductor. And then we have auxiliary transformer here. From auxiliary transformer, we increase the voltage until 150 kV in substation solar panel. And then we transmit the power to converter station. Here, rectifier. This is converter station. So from rectifier, we can transmit the power through cable or conductor to inverter. So we do not have problem with distance here. The same for turbine, cluster turbine. We connect through a submarine cable to AC collector station. From AC collector station, we send the power to converter transformer and then connected to rectifier. And then from rectifier, we are using DC submarine cable to transmit energy to inverter, which is located in AC substation. So if before we are talking, we zoom about AC platform here. This is example a DC platform. So once again, this is cluster turbine. We transfer the power to AC collector station as per the drawing previously. We transfer the power to converter station or platform converter station. In platform converter station, we have rectifier. From rectifier, we transmit the cable, the power through DC submarine cable to inverter, which is located in onshore. What is platform DC here? Typically, this is the design when we have typically 800 or 900 megawatt. We have the size of platform 60 times 90 meter. All this very big size of platform located in offshore. When we design, we have to consider sea cycle for 100 years, and where the sea level can be increased between 20 to 20 meter, 20 to 22 meter. And also piling here quite depth because the platform here the weight is very big. Dolwyn 3 platform, DC Dolwyn 3 platform, year operation 2020, nominal power 900 megawatt, 320 kV DC, AC collector 2 VSC platform 150 kV, here 150 kV, the distance wind power to the land 80 kilometer. So we have longer distance now compared to AC. Number of power plant area 3 cluster. So when we produce until 900 megawatt, normally we have many cluster turbine. For number of turbine 206 unit, capacity of turbine per unit between 3.6 until 5 megawatts. The sea depth here between 27 until 29 meter. So now we move to design. Objective to design and simulate the characteristic of converter from variety environmental condition. The study carried out during project execution before installation to ensure converter station operate in as per design. So here typical engineering study during construction. All study to be done before equipment delivered or before energization of converter station. This typical engineering study is not same from one project to the other, depend on the requirement. The project owner sometimes need more study, and then the other owner maybe need less study. Load flow study to describe active and reactive power, transfer capability to the converter station. Transient study to obtain transient stability of AC system with HVDC control system coordination. Quality of power and AC harmonic analysis to determine whether the harmonic generation by converter within the limit. Insulation coordination to determine the insulation coordination of all equipment at the converter station. Valve converter to determine converter valve detail, valve topology, or order number of valve submodule, valve main component. HVDC protection strategy to define the DC and AC protection component and the function of converter station. Main circuit parameter to define the range of operating condition of the FAC scheme and the major component rating. TOV to determine the transient overvoltage and the current stresses on the major converter station equipment. FFTOV to determine the performance of control system when responding to load rejection or when the converter is blocked. Recovery after fault to review the converter control capability to restore the active and reactive power to the free fall value level within a certain interval time after transient short circuit fault. DPS to verify the transient and dynamic performance of VSC when operating condition of power grid changes or when disturbance occur on severe condition. Multi-infit to review the VSC converter station performance along with network when interacting with other HVDC converter station. Noise level to prove the design of converter station lower than limits specified by requirement. Radio frequency interference to evaluate high frequency interference generated by converter station, EEMF to prove the electric and magnetic field at the converter station do not induce current, leading to overheating in other important equipment, black start capability to prove VSC converter station is capable to supply power to area where the power grid is not available. Island operation to demonstrate the converter control system has an ability to detect any of converter station disconnect from other converter station. Calculation of electrical losses to calculate converter station and transmission losses during converter operation. SSTI to dampen oscillation occurring when an AC generator operates close to converter. The subsynchronous damping controller system, which is part of VSC controller, to dampen the generator torsional oscillation, which can be created by converter station or AC generator operating close to converter station. POD, the objective to dampen oscillation occurring in the AC substation or AC system, can be between generator to local AC system or between one generator to the other generator in power plant area. POD, which is part of VSC converter control system to dampen the grid swing when the power frequency of the AC system is low. RAM, the objective to design converter station to perform better. What is the RAM here? Reliability, objective probability to transmit electrical power without interruption within certain period of time. Typically, measurement of duration of number of disturbance can be divided into two. One, total duration disturbance with two conditions, force energy unavailability or schedule energy unavailability. Or the second one, we measure through number of disturbance, either each pole or bipole within 1 year operation. Availability to deliver, the objective to ability to deliver an electrical power during 1 year operation. 1 year operation equivalent to 8,760 hours. Example availability calculation, we calculate the number of operating theoretically 8,760 minus force energy unavailability minus schedule energy unavailability. While for M, maintainability, maintenance schedule in order to deliver an optimum power. There are two activities here. Schedule maintenance as per operation and maintenance manual equipment, or unscheduled maintenance. By this, we have to do corrective maintenance in order to limit disturbance. We can put maintenance service 20/7. So now we move to factory to test. There are 4 types of tests: factory test, site test, trial operation, warranty period. Factory test to be carried out before VSC converter station equipment is delivered to site. Factory tests provide opportunity to discover and correct possible equipment error. For main equipment, sometimes factory tests will be witnessed by customer. There are 2 types of factory tests, routine tests and type tests. Routine tests objective to confirm operational performance of equipment. For certain and main equipment, routine tests actually will be attended by project owner. For what is the main equipment? For example, control and protection routine tests. There are 3 types of tests for control. individual control and protection. We test cubicle and software individually. And then next step will be F8, FST, and then the last one, FAT. What is FST? The objective to verify control, protection, and monitoring function operate correctly. Normally, we are doing all the cubicle to be tested by in FST. FST is an internal company test, so we only doing internally. When we have completed successfully, we will invite the client for FAT, factory acceptance test. FAT test only by selecting panel as a sample to be tested in order to reduce interval time test. Otherwise, it will be longer for customer to stay. Project owner or representative normally attend the FAT test for control and protection. Type test to verify prototype of equipment. Type test is different from routine test. Type test normally carried out by independent laboratory, and type tests sometimes require long duration and considerable cost. For main equipment, the type is mandatory during project execution. For instance, for converter valve and converter transformer, there are certain type tests should be carried out. And then for the rest, only to show a type test certificate from the previous project. Now we move to site test. There are 5 types of type tests: pre-commissioning, commissioning, energization, trial operation, warranty period. For pre-commissioning, we have two types of tests to be done: individual equipment and pre-commissioning subsystem tests. For the pre-commissioning individual tests, to test individual equipment by equipment, while for subsystem tests, to test more than one individual equipment or more than one, or if function related to each other. For instance, here, commissioning AC substation with converter station, or converter transformer and with valve, pre-commissioning protection test, pre-commissioning switchgear sequence test. Commissioning to test when transferring active power, or transferring active or reactive power, or active and reactive power to the network. So for commissioning, depend on the availability of the power. Sometimes the test for commissioning only to transfer active reactive power. For energization, to test converter station capability to transmit electrical power from minimum until maximum or nominal power. Once again, depend on availability of power. If converter station located offshore and onshore, onshore and offshore, energization always starts from the onshore substation. There are 3 steps of processes here. The first step, we have to energize onshore converter station in start-com mode. The next one, we energize offshore converter station. And then the last one, we energize offshore wind turbine and submarine cable. This is example of the circuit here. For the first step, when we energize in start-com mode, we close circuit breaker, which is connected to AC substation in onshore. This connector here still remain open. There is no connection to offshore converter station. So when this circuit breaker is closed, we can energize converter station offshore in start-com mode through pre-inserting resistor here. So when we energize here, valve here, converter is set to the block mode, and we raise the voltage up to nominal voltage. So by this, we energize onshore converter station. The first steps finish, and then we move to next steps, energization offshore substation, converter station. So when we finish energize in STATCOM mode, CB1, CB2 still remain closed. And then now we close all this connector here, this connector 1, 2, 3, 4, including circuit breaker connection connected to converter transformer, we close, while CB4 or CB5 connected to wind farm still remain open. So when this connector close, the energy will flow to offshore converter station. So by this, we energize already offshore converter station. When energy converter station offshore energy be energized, offshore converter's valve is set to the block mode, and then we can raise the voltage until nominal DC voltage. So by this, the second stage is completed. We move to the next one, the latest one, to energize offshore turbine. So we did already energization onshore, we did energization offshore. So all circuit breaker here, circuit breaker 1, 2 still remain closed. This connector remain closed. CB here remain closed. Now we close CB4 and CB5. By this, we energize wind farm, we energize wind turbine and transfer power. The transfer power here, the purpose only for auxiliary power in order to help turbine to energize themselves. So we will not transfer big power to turbine here. This is only for auxiliary supply. Trial operation. So we have to make sure converter station in good operation before handed over to owner. So typically for trial operation duration between 2 until 6 weeks, but between 2 until 8 weeks. If there is no major problem, there's no major fault, so we can transfer officially converter station to the owner, and then we start warranty period. The objective here to guarantee operate converter station operate properly. Typical duration warranty period between 2 until 3 years. Some depend on the customer. Sometimes customer asking until, let's say, like 7 years, depend. This is only typical. Example, warranty period evaluation, how to evaluate. Either the evaluation to measure minimum transfer during 1 year operation, or minimum power transmission during 1 year operation, plus in case any total number outage can be tolerated during 1 year operation. Let's say if the requirement only 5 volt, but we have 6 volt, by this in the year 1, we fail to meet the warranty period requirement. So now we move to economic comparison. The objective here, cost comparison for project 500 kV, 3000 megawatt for overhead line transmission for 1,000 kilometer. Because until now, there is no VSC with the rating 3000 megawatt, 500 kV. So we just take comparison for cost comparison between SVAC and LCC HVDC. There are 4 steps calculation here. First step to calculate substation cost. The second one, transmission cost. The third one, right-of-way cost. And then the fourth one, losses or benefit. For substation cost, by having 3,500 kV, the assumption we have 3 diameter 500 kV substation, the cost 60 million, while for converter station, we consider 500 million US dollar. And for transmission line, we need double circuit for AC with the arm 26 meter and with the total height of tower 76, while for DC only 18 meter arm and 47 meter tower height. So in order to compare, we have 4 parameters here: conductor material, tower foundation civil works, insulator side wire, project management, engineering, transport installation with certain weighting factor. And then we get the figures here: 1.3 transmission cost for 1 kilometer, and then we got for 1,000 kilometer. We do extrapolation from AC to DC based on the number of tower. We get the figures 800,000 US dollar per kilometer, and then 823 million for 1,000 kilometer. For right away, there is a different requirement from different countries. Sometimes some country they ask to release the land just under transmission line, and then to pay also the land surrounding the tower. But sometimes they only keep asking for to release the land surrounding tower. So we make assumption here. We only consider the arm of the AC or DC. And then we get the figures here with 10,000 kilometer. So our right away, 371 million for AC, 257 million for DC. So for 3 calculation, we have the amount here. So for AC, actually from this table, we can see AC for HVDC construction cost is cheaper than AC, HVAC, about 11.6%. From the diagram here, by rule of thumb, we can see AC substation cost in the beginning very low, while for DC high because we have cost of converter station, but because of the transmission cost and right away cost for DC smaller, at the end for 1,000 kilometer, you can see here we have 11.6% cheaper than AC, while for based on rule of thumb, normally they said the break-even cost normally within 700 kilometer for overhead line, and then between 40 to 50 kilometer for cable. And then for the losses, by making assumption, this is the transmission losses. For transmission losses, we have 426 megawatt, and for HVDC, we only have 290.6 megawatt. And for substation costs, we assume same because we are using the same AC substation. This is the losses of power converter in AC substation. Converter losses here, we assume 1.3%. This is quite big, but this is only assumption. So in the total, we have 78 megawatt. And transmission losses from here, we get the total losses for AC, SVAC 435, while for SVDC only 299.6 megawatt. So at the end, SVDC losses is lower than SVAC, about 31.8%. So if losses, when we convert to the money, by assuming penalty losses during project lifetime, let's say like 25,000, this amount, we get penalty evaluation losses for HVDC 1 billion, while for AC only 742 million US dollar. So if we combine here project construction costs from previous calculation and penalty losses or benefit between AC and DC here, we can see HVDC, the finance overall cost, construction and losses, HVDC is lower than HVAC by 18.95%. This is only estimation, while based on SIGRE working group, April 2020 to 2012, we have to consider uncertainty costs between 15% until 30% in calculation in the project reality. Project reference list. Until today, in operation, about 9 offshore project reference lists, all in German, with power range between 400 until 900 megawatt. DC submarine cable distance from land between 45 kilometer until 159 kilometer. The first offshore VSC in operation, it was 2010. There are 8 offshore ongoing projects today. It's being constructed in Germany and UK, and then 1 solar energy VSC project in Japan. In the future, more than 20 offshore VSC projects will be built in many countries: Germany, Netherlands, Denmark, UK, US, and other countries. Some future projects will have power up to 2,000 megawatt, while today only maximum 900 megawatt. From this presentation, we can see renewable energy, wind farm, and solar energy will continue to grow in the future. Therefore, VSC for renewable transmission is needed in order to maintain stable electrical network. On the other hand, based on our calculation, HVDC makes more economic sense than HVAC for long transmission distance. That concludes my presentation. Thank you. And I know that today's topic may bring up number of questions, and I will be happy to address as many as I can within time that we have today. Thank you. I hand over now to Emilia.
Hi, Terklin. Thank you. It's Alison here. If you'd like to go and have a break now, I shall share some slides. Some people have been asking about CPD. So if you want to go and have a break, and then for Amelia can let me know when she wants to come back in. It's about 5-10 minutes.
It's okay. Yeah, no problem.
Okay.
Okay.
And then I'll let everybody else know when you're coming back. So before you go, Terklin, before you go, can you stop sharing your screen?
Okay. Oh,
so I can share the screen, my screen.
Yeah.
Thank you. I think you're still sharing your screen.
Oh, strings.
You stop. Click on the middle, on the bottom where it says stop sharing screen. I don't think I can do it instead. In the middle of the screen at the bottom, there's a rectangle with an arrow pointing upwards.
Did I still?
Yeah. I'm going to try and share my screen just to see if I can overwrite it.
Yes, Alison, just try. You should be able to.
Thank you, Amelia. Is it coming through? It's looking a bit strange for me. I think you're still sharing your screen. Can I stop sharing it?
You're sharing the screen?
No, you're still sharing your screen. I can't stop sharing. Stop my sharing. I can't.
No, I stopped already screen.
That's it, Alison. You're okay now.
Okay, thank you. Right, so if you want to turn your camera off for you to have a break, Terklin.
Okay.
Okay, so thanks again, everybody, and thanks for all your questions. We have tried to answer some of them as we've gone along. I will just share some of the slides. Hopefully I can put myself in there.
Hello, Alison.
I've just gone off. Can you still see my screen now?
No.
Okay, I'll share it again.
Yes.
Yep. So you can see the local area network one with the train, with the tram on it, can you?
Yes.
Great. Okay, it's just that it's not showing in my window like it was before. Okay. So if I do 5 now, the presentation. Okay, so I've turned the automatic change slides off. So I'm just going to go to the slides that you are asking about. So this is the upcoming event. The web link, I thought I'd turned the slides off. Okay, so that's the upcoming event. The QR code is there and also the web link. But if you go to the, I'm crazy here. I'm just going to take it out of our presentation mode because it's got that automatic slide changer on. I didn't write these slides myself. So this is the upcoming event. It is on autonomous vehicles and the ethics of them, and you can see it from the community's home. And I'm going to put that in the chat. Chat now. Find it when I wasn't on today. Okay, to all attendees. So there's the link for the next IET Northwest Midlands event. And then we've got a British Computer Society event also. And that one is on the 9th of February at 7 o'clock. And it's AI for digital forensic investigations of digital media. Now I'm going to be interested in that one as well. And I'm going to put the link in the chat here. So this is the BCS event. By the way, if you've got any more questions that you can think of, carry on asking away at the question and answer. We're going to go to, I think we did find the link for the CPD. I found it somewhere. We've shared it a couple of times. So I've shared it. I just can't find it at the moment. Much easier to share things when you're not live. I don't know if somebody else could share that link for me.
Yes, don't worry. We'll put it on chat. And
I did find the link for the discussion forum as well. I will, please, if you do want to ask any questions after the event, or any of your questions haven't been managed to be answered during the event, you will be able to see it on the discussion forum. Now, Sam has kindly created this HVDC voltage source converter technology forum. In fact, that was October 20th. That's not the right one, is it?
It's okay, we can use that one. That was created. Yeah, that was created for part 1. So since this is a continuation, we can always continue with that one.
Okay, so I'll any I can't type answer. Then okay, so we got that. So I'll just go back to the PowerPoint that we were doing before. I shall put it back in PowerPoint mode. So thank you again for coming here tonight, and much appreciated. And I hope you've enjoyed Terklin's exciting talk about HVDC and the wind power, because we're all interested in having zero carbon footprint. And he'll be back soon. We do have a good, healthy list of events coming up this year, and as we said at the beginning, hopefully we'll be able to get some in live, but if not, we'll still be here on Zoom. And the good thing is that we can also record them as we go along and make them available on our YouTube channel. Thank you also for your attention. And there's a couple of new questions that have come into the Q&A. I think it's about part 1. I've got questions saying, is it about part 1? I'm not quite sure what that question is. We'll look at that first. We'll discuss that in a bit. No. Okay, so we'll see. I don't know if you want to get a quick break. Do you know how long Terklin's going to be? I didn't notice what.
Yep, we can check if he's back. Terklin, are you back now?
Yes, I'm back.
Okay.
Excellent. Okay, so I'll hand over to what's going to happen now is the questions that you've been asking in the Q&A. Then Amelia is going to ask Terklin those questions and he will answer them for you. Okay, so hand over. Thank you very much.
Thank you. Terklin, you can kindly switch on your video. Thank you. So I'm just waiting for Terklin to switch in his video and then we can start. Yeah, thank you, Terklin. Once again, Terklin, thank you so much for your presentation. There've been a lot of positive comments. People have been very grateful for the presentation you've delivered. The first question that I'm going to ask you that has come from Craig Johns is to do with one of your first slides, your initial slides. He was saying for wind, why do we need to convert from AC to DC and then back again to AC? Is this always the case?
Okay. Can I share my slide now?
Yeah, if you want, you can. Thank you.
Here, this is the question here.
Yes.
So actually, why we always need DC here for, okay, back to the theory before. Before, when we have in the first generation of turbine, we don't have here, we don't have converter here. So when we don't have converter, actually, you are right, the question here, we can connect directly here between turbine two AC system? This is the question. But this is only used for, we can say, small size of turbine. Because the problem here, if we only have direct connection, imagine if we have a problem, let's say like a fault right through. There is no bumper here, no bumper to resolve the problem here, to resolve the problem, because everything output here connected, absorbed by AC system. This is one question here. And then the second one, the synchronization. We have to consider whatever we produce here, if directly connected here, it will be not, the performance will not be good. So that's why today, for high voltage or for higher capacity, we don't use anymore direct connection here. We always use here either partially through, okay, this is actually the second one, but mainly today we have partially here, rotor connected through DC converter, and then stator directly connected here in order to meet fault right through. But again, here, we can say for medium size, most of turbine, the high size, let's say like for turbine used for offshore in Germany and so on, today we are using variable speed fully connected to converter. So for this, for right through, once again, to meet the fault right through. This is the purpose, to connect turbine through converter. This is the answer.
Thank you very much. I hope this answers Craig's question. The next question is renewable energy that you shared is more for European or Western side. What is the trend for renewable project at Southeast Asian or Asian side?
Good question. This is very generic question actually.
Yeah.
So based on experience today, actually you are right. The market only mainly in Europe and US. So the rest of the world actually not starting, especially if we are talking about VSC. Why? Yeah, there are many possibilities. One possibility, because the cost is very high. And then the second one, if we see here, when we are talking about grid code mostly today really we can say mature in Europe and US. So if we don't have a, let's say like a quite strong grid code, maybe offshore will not be working. And then, to build offshore converter station, very complicated, because the converter platform will be located, if we see here from the drawing here, this platform very heavy. So one platform can be, let's say like 11,000 ton. And then when we build in the middle of sea, if we do not have a quite good study, and then also about the budget, so we do not expect the project will be there. So what we see today, mainly why the project located in US or Europe, because grid code once again more advanced here. And then here the customer also quite mature. They know the system should be strong and good. By this they can install offshore. While for the other country, let's say like for South Asia, basically we are talking about Indonesia. So the risk is there. So most of investor or utilities, they are really still bit hesitate to build offshore converter station. This is only the answer. So I agree with you. Today the market mainly only in Europe and in US only. But in the future, of course, there is still possibility, because when the people want to invest the money and then we have a strong engineering base, There is no limitation to build converter station, offshore converter station, let's say like in Malaysia or in Philippines or in any other Southeast Asia countries.
Thank you. So I'll take you back to the costs. There was a question on costs. So the question is, how do the operating costs compare? For example, inspection and maintenance of VHAC and HVDC solutions.
Oh, for maintenance costs?
Yeah, as an example, yeah, maintenance and inspection.
So if you're talking about the budget here, yeah. So budget actually, this is not considered here. We are talking about investment. So we are talking about maintenance costs. Maintenance costs, roughly 1%, we can say about 1% per year from investment costs. So there is no direct or straight answer to compare between AC and DC. But in terms of component, we can say today, for instance, for converter station for valve, and then for a converter transformer, we have lifetime, for instance, for 25 years. Maintenance cost is very low, we can say. And then the probability to get damage for this equipment so far still low, we can say, even though for VSC, the start operation only by 1999, yeah, about 21 years to come for until now. But most of converter station, which is built in the beginning, in first generation, until now still working well. And then in terms of operational costs, not so much, not so high. The same for AC substation. If we are talking about AC substation, quite mature technology. So comparison will not be apple to apple because the component will not be same. For VSC, we are talking mainly for converter valve, converter transformer, and DC equipment. But for AC, different from DC substation. This is what I want to tell here. So the different here, different component cost, but average we can say AC and DC mainly we have the same, not so high, not so much operation cost per year.
Thank you. There is, looks like interesting questions on costs as well. So the question is, are life cycle costs taken into account with the cost that you discussed in part 10?
Yeah. We are talking about the losses. Yes, correct. What is the question here?
Are life cycle costs taken into account with the cost discussed in part 10?
Correct. So when we see the slide here, so this is because this is actually used for investor when they want to build either converter station or AC substation, they have to consider, first of all, construction costs and also penalty costs. This is losses, penalty losses or benefit. So for how to calculate, actually what our assumption here, this is we can say the standard penalty losses for lifetime. Let's say like when we build converter station for 25 years, or when we build AC substation for 25 years, we have to apply, we have to have one point in order to compare one to the other. So here, this is penalty losses for lifetime project. Let's say like the losses $2,477.9 per kilowatt. So by applying this to the total losses of AC and the total losses of DC, we got the total, we can say the total investment cost for investor to pay actually. So that's why when we compare actually, not only construction costs, also we have to convert we have to compare also the losses which has been created by these two technology, AC and DC. Therefore, in my calculation, when I get the total losses of AC 435 and I got the total losses of DC 299.5, I have to meet the similarity, how to transfer these losses into into money for the investor. So by this, there is a convention. This is the actually the industrial practice for lifetime. They can use 2,500 or can be 2,600. This is depend on the convention used here. But in my assumption, I put 2,400. By this, I can compare what is the monetary losses of AC, what is the monetary losses of DC. I don't know if it is answer the question here.
Thank you, Terklin. Are you okay to continue answering questions?
Maybe one or two more questions after that. Maybe we can go. We can answer by Q&A, as I mentioned, because the time is now quite late.
Okay, all right. So there's a question on solar panels. So the question is, which one is most efficient electrically on the connection of solar panels, in series or in parallel?
Oh, yeah. So today, the main most of connection using series connection. This is the right answer.
Okay, thank you. There was a question as well on connection of wind farms. So it was, what's the difference between radial and star configuration?
Radial and star here.
Yes.
Good question. Actually, the radial, the star here, this is the most expensive, the most expensive cost. The most expensive cost because we have cable to all to turbine here. While for radial here, we have connection for in certain, let's say like if we have a cluster, we have cluster 1 and we have cluster 2. So we only connect the cable based on the cluster here. While here we connect the turbine based on the number of turbine here. So we need more cable here, more cable for connection in star. So that's why in star, not based on experience, not so many turbine configuration using star connection. Most of configuration today between ring and radial.
Thank you, Terklin. I'll push you for one more question, if you don't mind.
Okay.
So for wind farms, what are the reasons for choosing a combination of DC? It says AV here, but I think it meant AC. So the reason behind choosing a combination of DC and AC transmission for an offshore wind farm.
Good question. Actually here theoretically, because until now there is no project having combination here. But the reason here actually mainly reliability. Reliability, when I say here 50% group in transmitted power. So reliability, in case we have problem for DC connection, we still can transfer the power through AC here. The same, if we have problem for AC, we can transfer the power through DC because we are using the same cluster here. So until now, there are no project exists here, but there is still possibility if the client want to maintain very high reliability, they can use the connection. This is almost same as our first presentation in November when we are talking about bipole and one single pole, monopole operation. So by bipole operation, we have more reliable compared to monopole operation. The same here, this is mainly for reliability.
Thank you, Terklin. Thank you very much. I think we did mention in our first presentation, which was done in November, that if there are any questions that we have not answered tonight, we will endeavor to answer them on the forum. I am aware that right now on the part 1, there are no answers as yet. We'll combine the answers with the answers from today, and we'll make sure that the answers are posted on the forum. If there are further questions, we can always discuss on the forum. At this point, I would like to thank you so much, Terklin, for taking your time to educate us and enlighten us on VSC, HVDC, and renewable energy. I'll hand over to my colleague, Berna Mustafa, who's going to do the vote of thanks for us tonight. Thank you.
All right, excellent topic. Thank you once again, Terklin, so much about the hot topic of nowadays of HVDC technology. You delivered an insightful information about it, and it's basically a major. It will play a big role into, connecting more renewable sources to the power grids, basically. Thank you, Emilia, as well, for dealing with the questions raised from the audience, as well as thank you, Alison, for leading this event. Probably you've seen already that we provided a couple of links. So one of them is for our IET Northwest Midlands website, and also the forum where we will publish the unanswered questions. So please do check them in the chat box. Also obtain your CPD certificates. I think there's a slight problem with the certificates, Emilia. Probably we have to revise it because I've seen comments that people can't write their names down. So again, please download them, but we will make sure that they are working and come back again to download. So,
okay, we can check into that and perhaps update on the discussion forum, right?
Exactly.
Thank you.
Yes. Yeah. So again, yeah, please do check the IET Northwest Midlands website so you can see what we are doing here, the Northwest Midlands community. And yeah, the link is provided again in the chat box. We've got other upcoming events. Again, this is provided in the chat box where it says upcoming events link. There also we've got a YouTube channel, which is IET Northwest Midlands. So please do go check the YouTube channel. And for those who missed the first part of this topic, again, VSC HVDC technology part 1. So go there and watch it. So for some of you, it might answer some of the questions you already have and you did miss on this part too. Right. Again, Terklin, he's writing a book actually about this, and we are planning to publish in the forum the information about from where we can buy and download his book once it's ready and translate it in English, so you can learn further of the topic, basically. And thank you so much for attending this webinar. We had a great audience and some amazing questions in the Q&A session, and we will expect you to in the new events that we organize. Thank you so much. Thank you for attending. Bye-bye.
Thank you.
Thank you.
Okay.
Thank you. Bye-bye.
Bye bye.